Hey everybody, welcome to today's Byte session. Here we have Josh, and he's going to help you learn UNR.
Awesome. Thanks, everybody. All right. Yeah, like Nathan said, my name is Josh. I'm currently a software engineer working for Stripe. Previously, before that, I worked at Google. Happy to take any questions if you want to talk about that later. But today, we're not going to talk about any of that. We're going to talk about my hobby, which is data science and statistics using R. So I just want to explain a little bit before I get into the presentation of R itself, like what R is, like why would you want to use R, what's interesting about it. Usually when people talk about R, you hear the terms like data science or statistics, right? These are kind of words that people throw around. These are things you'd use R for. But since this is a data science, presentation, I decided I'd make a chart. So here we have a chart of programming languages, compared to how specialized they are and how mathy they are. So down here in the bottom left-hand corner, in the sort of general non-mathy programming languages, you have like Python, right? Everyone knows Python, you use it to write websites and stuff, right? But like if you put NumPy, if you use a NumPy library, you get like a little bit more mathy and a little bit more specialized. So you get some syntax that's kind of like what you'd expect in math. And then Python becomes a little bit more useful for specialized applications. On like the upper right-hand corner of this chart, you have something like Wolfram Mathematica, right? A programming language that's like purely designed to match math as close as possible and be used for like advanced mathematics. And then, a little bit less mathy and a little bit less specialized is like MATLAB. People use that in industry to do like simulations or, whatever you want to do. The syntax still matches math syntax pretty closely, but, and it's not really something you would use to do like general purpose programming, but it is less specialized than like Mathematica. Like right in the middle, I've put R because R is sort of an in-between. It's not as mathy as something like Mathematica or MATLAB. It's not as general as something like Python, and you still use it to do some specialized stuff, but it is more general, more friendly to like a normal programmer. It's not too weird, although we'll talk plenty about the weird things about R in this presentation. Another interesting thing about R is you can think about programming languages on a spectrum from being like imperative to being like functional. So imperative languages are like C++, Python, Java, typical languages that most people use for writing applications. Very procedural, you have like while loops and statements, right? Versus something more functional like Haskell, where everything is a function. You don't have while loops, everything's done with recursion, etc. R is kind of like in the middle here, right? It's sort of functional. It's got a lot of functional features. You tend to write a lot of functional code, but it also has more of the friendly imperative features that you would expect in a language like Python. Yeah. All right, before I get into the code here, I just wanted to give a little more context about R as a programming language because it's pretty weird. It's very old. So R was a successor to a programming language called S, which was developed at Bell Labs around the same time as C. So it is very, very old. Like R's implementation is 30 years old. It has a lot of like the properties of a 30-year-old language like C or C++, in that there's a lot of them and they don't all work perfectly well together. So there's a lot of little exceptions and special cases that I'm not going to cover in detail in this presentation. You could spend an entire presentation just talking about the exceptions and little details. So anyways, it's an interesting thing that has it's been around for a very long time. And it's actively used by thousands of people to do like real work every day. So every company that I've worked for has used R internally for like actual data science applications. Stripe, the company I work for right now, they use it to do, analysis of financial data and to, power their services. So it is like a real thing. People really use it in production all the time. Let's just get started, get onto the code. So I'm going to start with like the very, very basics of R, and then we're going to build up to more and more complex examples that teach you about the interesting things about R, what makes it unique. So when I say basic, I mean really basic. We're going to start with Booleans, all right? So R has like Booleans, true, false. You write them like this. This entire slide presentation is based on an R notebook or a Jupyter notebook. So this is like a code block in the little highlighted section, and then the output is right below it, so you can compare what it is. So in R, you write true and false, all caps. It's a 30-year-old language, so it's got some weird idiosyncrasies like that. It has numbers, negative numbers, positive numbers, floating point, whatever you want. All right, it's got strings. You can use double quotes, you can use single quotes. You can do math. You can like add numbers. There's all sorts of operators for doing different kinds of math. Like Two unique ones in R is like this exponent thing. In Python, you can use double asterisks, but in R, it's just like a regular caret. So that's 2 to the 8th power. And then the double percent is modulus. It's 2% instead of 1. And I'm not going to explain why, but there's a really interesting reason. All right. R has variables like every other programming language, but it has a really weird syntax for variable assignment. Variable assignment is done using this little arrow. You can think about it just like an equal sign. That's just assigning 42 to a variable named myVariable and printing out the result. It has functions. They work like every other language. You can even define your own functions. R is a little bit more like JavaScript or modern JavaScript in that you don't have like function introducers or function declarations. Instead, you just have anonymous functions that you assign to variables. So here we're declaring a new function called say hello, takes in a parameter name, and then we're invoking it right below to say hello hacker refactor. Great. All right. R has like the super typical control flow that you would expect in like C, Python, Java, whatever. It has if statements. It has while loops, for loops, etc. All right. But there's a really, really, really unique thing about R that I haven't talked about yet, and that is the way that vectors work. So in, a vector is R's name for like what in Python you would call a list, or what you call an array in Java, C, JavaScript, C#, whatever, or vectors in C++, same concept, right? Just a kind of a set of data elements, usually all the same type, nor they have to be the same type. And the interesting thing about R is that everything that we've already talked about today is a vector. There's no scalars in R. Every single thing is a vector. So when you write the number 10, that is actually a vector containing one element, 10. Same with strings, same with Booleans, right? So here I've showed you, I've used this function length to show that all of these are actually one length vectors, right? Even though we just wrote them out like that. This is where a lot of like the power and interesting things about R come from. And also it's like very surprising if you're not expecting this. But, oh yeah, also, we talked about how to make one element vectors, but if you want to make longer vectors, you just combine other vectors together because everything is a vector. So you can use the C function combine, which combines all of its inputs into a single vector. So this first line is the element or the vector 1, 2, 3, 4, 5 written literally. And the second line is the ABC, a vector of 3 strings, ABC, written literally like that. And you can see, like, if you take the length of this extended vector, you get 5 like you expect. All right. And just to like really drive this point home one more time, that we're just combining vectors together. We're not like writing a list. It's different than like a list in Python. We're combining vectors. Here I've like nested a combine. So I'm passing a combine into another combine, and you can see it just makes a single vector, right? It's just concatenating all the elements of the vectors together. That's all it does. So there's no nested vectors. You can't have anything like that in R, just kind of basic types. And, I said we could do math earlier, right? But in R, everything is a vector. So we can actually do math on vectors. That's pretty cool. So all of the operators in R out of the box work on vectors. So here I'm doing a vector multiplication, multiplying 5, the vector 5, that's a single element vector, against all of the elements. And I'm taking in all the exponents of 2, all the powers of 2, the first 8 powers of 2 in the second line here. And so yeah, just like it works element wise like you would expect. So it takes the first element and maps it over each element of the vector you're using the operator over in both cases here. You can also use multi-element vectors. So if you have more than one element in each vector, it will go element wise across both of the input vectors. So here we're like adding 2 vectors of size 2, and we're adding the first element, second element to get 4 and 6. And it even supports generalized broadcasting, as they call it, which is like something you can do in NumPy, where you can do math over vectors that aren't the same size. And R does this by repeating the smaller vector. So here you can see that we have a 2-element vector and a 4-element vector, and the 2-element vector is extended when we're doing math. So there you go. All right. So that's pretty exciting, pretty interesting. But where the real fun begins is when we talk about indexing vectors. So I'm going to use this example vector for the rest of for the next couple sections. Actually, just this one section. This example vector, it's just arbitrary. I picked it randomly, but we're going to use the same vector. I'm going to print it multiple times. It's not changing, so just there for reference if you don't get it. So in R, you use square brackets to index a vector. We start with 1 here. So 1 gets the first element of the vector. Sorry, everybody, that it's 1 base and not 0 base, but you'll see more why in a minute. So we can see here, yeah, indexing the vector with 1, our example vector, gives us 1, the first element of our example vector. But remember, that's actually indexing the example vector by a single element vector 1. So what happens if we index with like a longer vector, right? You can do that in R. And the answer is you get all of the elements that are in the vector you're indexing by. So like here we get the first, third, fifth, and seventh element of our example vector in a new vector right below. That's pretty weird. That's unusual. And negative, you can also index by negative numbers like you can in Python or other languages. But in R, that's a filter. So if you index by a negative, that selects every index that is not in the vector that you specified. So not index 7 here, that's the 100. You can also index vectors in R by Booleans. So the way that you do this is you give a Boolean vector that's the same length as the vector you're indexing. And for each sort of position, it checks if the value is true. And if it's true, then the value is included in the output. If it's false, then the value is not included in the output. So this is just a vector of true, false, true, false, true, false repeated, which selects every other element out of our input vector here. And vectors are repeated if they're not long enough. So it will just repeat true, false, true, false, true, false in this case for the length of the vector. And that's useful for like, every other type of filter, something like that. All right. So kind of weird, interesting thing in R, you can use numbers and vectors or numbers and Booleans to index into vectors. But like, why is this useful? Like, why would I want to do this, right? And the super easy example is like using a Boolean filter to select data out of a vector, right? So here we have our example vector. And like, what if we wanted to get all the negative numbers out of this vector, right? That's kind of like maybe something we'd want to do for our data analysis. So what we could do is we could like, use a comparison operator to look for all the values that are less than 0, right? To find all the negatives. And that gives us a vector of false, true, whatever. And then we could just copy paste that into an index. Like imagine we copy paste that into an index and we could, get all the negative numbers, right? This is just exactly the same thing as I had on the previous slide. But of course, this is just programming, right? So we can just replace that in the index. So you can actually index by sort of any arbitrary Boolean expression that you want. So you can just select data kind of arbitrarily, and it does all of this kind of mapping over the values and selecting them under the hood. This is super cool. This is really, really valuable because you can just take this and you can just extend it to all sorts of like whatever kind of filtering you want to do. So here we go. Here's one that I have where I'm selecting all the outliers out of this data set, right? So I'm using this quantile function. Quantile takes like a percentile, in this case, the 90th percentile. So we're taking the 90th percentile of the example vector, and then we're just looking for any values greater than that. And that gives us 100, right? Super easy to do in R. You can also just filter for all of the non-outliers by looking for the outliers and then using the not operator to invert them. Really, really cool. All right. Last thing that we need to do, talk about in R before we can talk about how people typically do data analysis is lists. So lists is another basic concept. They're just dictionaries, hashes, associative arrays, right? Kind of what like a mapping of keys to values, right? You have a key, in this case, like Josh is a key and a value of purple, right? Mapping or like showing people's favorite colors. All right. And the $signs here, this is just a printing thing. This is just the way that R prints dictionaries, but the key itself is Josh and the value is purple. All right. You can index lists like a vector by passing in keys. So in this case, we're using these key names to index, and this just filters down to only the keys that you specify. So here we're just filtering to Josh and Brenna's favorite colors. If you want to look up like a specific value, the easy way to do that is to use this double bracket symbol or this double bracket operator. So if you pass in a string with double brackets, that gives you the value of the key. So here we're looking up the value of the key Josh, which is purple. And if you already know the name of the key, like it's not some variable, you can just write it out in code. You can use the shorthand, which is a $sign and then the name of the key to look up your value. So here we're looking up Josh's favorite color. It's purple. Same exact thing as the previous line. Lists can also work like arrays. We're not going to use them like this a whole lot, but remember how I said that vectors or arrays can only contain a single type in R. So you can use lists to contain multiple types of things. So if you're ever working with heterogeneous data or collections of heterogeneous data, then they're useful in that case as well. So you may see them there. All right, data frames. Data frames are like the most important thing and the main thing that you'll be using when you're doing data analysis in R. It's sort of the heart and soul of data analysis, as I was as I like to say. So data frames are a rectangular data structure. Okay, so you think Excel. There's columns, there's rows, and each row has values for each column, right? And in R, this is kind of like the main way that you work with data. Here I'm using this Pokemon data set. So I just found this online. It's just a collection of Pokemon and their different properties. This is a really big data set, so kind of doesn't fit on the screen well, but anyways, you get the idea. I'm using this built-in function, read CSV. This is just all standard R. Everything I've shown you today is standard R, built into the library, super easy, or built into the language, super easy to just read CSV files into data frames like that. I'm also using this head function that just prints the first 6 things because this is like really long data set. There's a lot of Pokemon. Data frames work a lot like lists, and this is why they work a lot like lists where the columns are the keys, and then like the value of a key is all of the data in a column. So this is why I explained how lists work. So here we're looking up like the names of all the Pokemon. So if we do Pokemon $name, that gives us all of the names of the Pokemon as a vector. And I'm showing that with length here. You can see how many different names there are. There are 1,000 names, 1,028 names, and we're printing the first 6. So because these are vectors, just like we already talked about today, you can index them like a vector, which is amazing. So I'm using this grep function here. When you grep for a pattern over a vector, it returns the indexes. So here you can see this first line here. This is the indexes of all of the values that match that pattern. And then you can just use those indexes to index into a vector and get all of the values, the full values that match a given pattern. So it's super easy. And you can index data frames like you can index vectors. So what we're doing here is exactly the same thing. We're just looking for all the Pokemons with the name that has char in it. And then we have this extra comma here because this is like a multi-dimensional sort of piece of data. This is just saying we want all the columns. So we're just indexing the rows is this first item. So anyways, this is when you can just easily pare down data to any kind of subset that you want to work with. And just to like show you an example of that, here's like finding all of the fire type Pokemon in our data set. If we wanted to look at just fire type, you can just use Boolean filters as much as you want to filter the data, really easy. Last thing I'm going to talk about today is a little bit of stats. So I feel like I have to talk about this because this is the thing everyone knows R for. As we've seen, there's a lot of interesting ideas in R, but stats, I think, is the thing that people mainly think about when they think of R. Full disclosure, I don't have a degree in stats. I didn't go to school for stats. I don't know stats. Everything I say in here is probably wrong. Don't trust me. All right. Just to like get our feet wet here, here's an example plot. So R has like very comprehensive plotting functionality built in, super easy to use. Here we're just looking at all of the different types of Pokemon, sort of filtering out unset types and then plotting out the frequency of each type of Pokemon. Pretty easy to do. We can also do like basic regressions. So as an example here, I have a plot of Pokemon's catch rate, or how likely they are to be caught. So higher catch rate means easier to catch. And then their HP. So higher HP is higher HP, obviously. And it looks like there's some kind of relationship here. If we just kind of look at the data, it looks like maybe easier to catch Pokemons have less HP and harder to catch Pokemons have more HP. But like in R, we don't have to just stare at the graph. We can run a linear regression over this to find the actual relationship between these variables. I'm not going to explain exactly how this syntax works, but it's one line of R using this LM function built into R to do a linear regression of HP as a function of catch rate. And here we can see that indeed there is a negative relationship between a Pokemon's HP and its catch rate of exactly 0.1623. And just, a couple extra lines of R, we can get an R squared, plot a regression line through our data set, et cetera. But, just to show you that how easy it is to do certain kinds of like statistical stuff in R. But like, I can do this in Excel, right? If I just throw this data in Excel and I make a little chart, I can get a regression line. I don't have to learn R. Like, why would I really, like, why do people like even use R at all, right? Like, why do they want to use it? And the answer is because R is like the de facto statistics sort of library, right? All of the statistics functions in R that I talked about today, they're like best in class, right? They're the ones that you want to use. And I don't know stats, so I can't really explain this to you. So instead, I thought I'd tell you a story about me trying to use R. So for fun, for work, I was working with this probability distribution called the gamma distribution. And I'm not going to explain what probability distributions are or how they work, but suffice to say that there are functions that have like input parameters. So here we're using the shape parameter, and they make these little graphs that look kind of like this. And the shape parameter changes how these graphs look. All right, take stats if you want to learn what any of this means. So I wanted to like find a gamma distribution shape. So this input parameter, I wanted to find one that had a certain 90th percentile in this graph, right? So here I've plotted the 90th percentile of shape 3, and it's 5, right? Roughly 5. But I wanted to find one that was 10, right? And these probability distributions, like these graphs, they're functions, right? So they have an algebraic form, and you could like do algebra on them in theory to like figure out what the 90th percentile was. So, you know, of course, I didn't want to try and like figure out that algebra. So I just went on Math Stack Exchange and I said, hey, is there like a form for looking up a particular shape for a given percentile? And they're like, no, there's no closed form solution for this. There's no algebraic form. The best thing that we have is an approximation. I suggest you look at R's implementation of its approximation because it's probably the best one there is. I thought, how handy for me. So a couple lines of R. I just went through, used this Q gamma function. That's the approximation that we were talking about before. So look up 90th percentile for different possible shapes. I ran 100 different shapes through this little thing, looked for the one that had the best accuracy, and boom, popped out 6.6 optimal shape. That's great. And look, there we go. We can plot it. We can use this shape. This is the exact same plot as before, but it's a different shaped probability distribution because we changed the parameter. And there you go. The line lines up right on 10. So not that necessarily made any sense, but the point I'm trying to make here is that all of these advanced statistical functions, they are just part of R's standard library. Every single thing that I just did here, that comes out of the box in R. All right. So that's all I'm going to talk about today. And I will say that everything I talked about here, this is just scratching the surface of what you can do with R, right? I talked about some very basic language features and some examples of stats, but there's whole other parts of R. There's like modern R style using pipes and the tidyverse and ggplot2. You can, these are things you would probably want to learn if you're actually using R for like real data science stuff. You can also, I didn't talk very much about functional programming. You can see how these operators are kind of functional and that they're mapping over data, but there's full suites of functional programming in R. I didn't talk about macros. R is kind of like a Lisp. You can do syntactical manipulation at runtime with it. That's pretty crazy. I didn't talk about object-oriented programming. R has 3 different class systems because, why not have 3 different class systems? You can use it to do like all sorts of other normal things too, like web scraping, or you can make websites. You can do anything you want in R. There's so much that it can do, but, I just had to suffice with what I could talk about today. So that's it. The presentation, the Jupyter Notebook, you can find it at this QR code or in the Git repo if you want to play around with it. There's a little link to open it in Binder, which will just give you drop you right into a Jupyter Lab notebook, and you can play around with it if you want. So that's it. Anyways, any questions? Thank you.
Do you really like R compared to other languages? Or what do you think?
So I've used pandas. I think the other languages that are very similar to R are MATLAB people talk about in R, but as a programmer, like someone who started with Python, like MATLAB is very scary and awful to me, so I don't like using it. But there are languages that are kind of like R. So Julia and then Python with pandas is pretty similar to R if you've seen that. I think pandas is great. If you know Python, you're really comfortable with Python, you should go with it. The reason I started using R, I actually started with Python and pandas, and then I switched to R just because of the statistical stuff. So the statistics packages in R, like the libraries that you can get, the tools that people have built, if you want to do anything complicated, it is just much easier to do in R than it is in Python. The other thing, I don't know too much about Julia, but I have heard people don't love it because it has had bugs in the past with its statistical functions, which people are that's a big no-no for data science. So that's all I know about it, but it seems kind of cool. I don't know.
If you were, let's say, just a resource or something for someone who wants to learn more about R, do you have a particular one on your head?
So I think there's this thing like if you just search for like our book, yeah, I think there's these books that like are have these nice websites that you can look through. There's like 3 of these. People in R has a lot of like built-in support for like running it and turning the output into like markdown files. So there's like really good docs. Like if you go to any like R package, so like here's dplyr. This is a like a really common R package, and you can just see like the docs that they have here. They have like these info sheets. This is like better than any doc that you would get in like any library ever. And this is like most packages in R. So just the libraries themselves tend to have really good documentation. And then for like practical stuff, I really recommend just like Googling your problem. And usually there's some data scientists that like ran into the same issue and they wrote like a really long thing where they go through step-by-step in R, like how to do the specific plot or like transformation that you're thinking about. So yeah, I just like Google R for data science, and that will get you started with the basic stuff. And then you know, you can go from there. Yes.
Do you use R much at Stripe?
Great question. So for my day job, not my hobby that I do off hours, but my day job, I work in infrastructure. So I build CI/CD systems for Stripe. So I use R generally at work to do kind of one-off data analysis when I'm looking at projects. So if I'm thinking about like, oh, like what is the, like if I want to chart out like the popularity of some feature, I have some data somewhere that shows how often people use something and I want to like plot that out, or I want to see how often failures occur or something like that. Yeah, I use it. Nobody else does. Right? Nobody on my team does. Nobody that I work with does. Like I mean, the data, there are data scientists that work at Stripe that do financial modeling, and they do like predictions for future forecasts and hedging models and all sorts of stuff like that. They use R all the time, every day. But like people I work with, software developers, no, not usually. I think it's really useful. Everyone should learn it, but you know, no. Yeah.
What's your favorite project you've done or are currently working on that involves R?
All right, I'll tell you my favorite one. During COVID, you know, everyone went a little bit crazy. We all got a little bit like more risk taking, I think. You know, everyone, you know, we got like we in certain aspects of our life became very defensive and scared of risk, but in other aspects, you know, took a little more risk. So I got really into sports betting over COVID. And I don't know anything about sports. I just like stats and data science stuff. So I was like, let's see if I can make any money like predicting basketball games on like daily fantasy sites. So I made a whole pipeline for like scraping stats off of stats websites and then like storing it in a database and then running like regressions on that to try and do predictions. And then running, I did like a linear optimizer to try and pick like optimal lineups based on the regressions. And like, I definitely lost like $30 doing this, but I wasn't very good at it, but it was pretty fun. It was a really interesting project to work on for sure. Anyone else have questions? Cool. All right.
I wanted to say that we're a few of us are doing machine learning. I know a few of us have already done it.
Yeah.
And we do it in pandas, but like pretty similar.
Yeah, pandas is like, if you know pandas, it's the ideas and concepts, like they map pretty well. It's like for the data frame stuff. There's this library, the tidyverse library called dplyr, this one that I was showing. Actually, I lost it here, but yeah, this library dplyr. It's like basically the same as pandas. Pandas actually, I believe, copied it from R, which is where that comes from. I would say Python is like probably the best language for machine learning, which is interesting because stats and machine learning are very related. So it's interesting that like Python ecosystem is very good for stats or for machine learning, and R is okay, but it's not as good. So, all right. Oh, do you have a question? Oh, sure.
School could, you know, bother you at all hours of the night.
I'm on LinkedIn all the time. Yeah, sure, absolutely. Yeah. You can also talk to Nathan and he'll get things to me. So yeah, either way. Cool.
Have questions about Skype or?
Yeah, I'm also happy to take or like software development industry, anything like that. I'm happy to talk
You
about.
also have the master's science at the University of Utah, so if you want to talk about research.
Yes, I could talk about research stuff too if you want.
Really?
Yes.
Give tips for like getting to a place like Stripe.
Do I have any tips for getting into a place like Stripe? So Stripe specifically, like I think Stripe specifically is very weird in terms of the way that we do interviews. It's quite unusual. So like I think it depends a lot on like the specific company. Getting into a place like Stripe, I think it's just like yeah, I don't know. It's more like practical than a lot of places. So we test people on like debugging, and we test people on like integration. So like writing, we have people like basically write a little web app as part of the interview process. So like just kind of getting familiar with like the practical aspects, like write a project, you know, find a bug and have to debug it yourself. These are all kinds of things that would help you get into Stripe. Yeah, I don't know. It's just the interview. I don't think there's any like secret sauce to it. But and I'm happy to talk more about that, or do mocks for people if you want, whatever.
Cool. You work remotely?
I do. I work remotely. I started remote at Stripe. Stripe has like, I don't know, a pretty big remote workforce. Almost all the people, it's about 50-50 the people I work with are remote. So we do almost everything like on Zoom, basically. And it works pretty well. I haven't had any issues or run into problems.
Actually, I have a question on that.
Sure.
Have you had like a in-office experience versus remote? Like what you like?
Yeah, so when I started at Google, I actually moved to the Bay, like to the Bay Area to like work there. And so I worked for Google for like 4 years in person, and then now it's been like 2. And then like a year and a half remote because of COVID, and then like I worked for Stripe, and it was I like the remote experience better. It's definitely different, and you have to take it really seriously. I think the thing that really sucked about being remote initially was that I didn't have like good work-life separation. Other people, it seems to be fine for them, but for me, I have to really have like a separate desk with like a separate computer in like a separate place that I don't touch unless I'm working, because any other kind of overlap, it just kind of spreads, and I just felt tired and miserable all the time. But like now that I kind of have like a place that I go in the morning and then I leave at night, and I also set up kind of boundary stuff like activities at night that make me leave work. It's not so bad, and it seems pretty normal for me. Yeah.
How?
Yeah.
This Google, do you like Stripe so much more? You don't work out?
So Google is huge. Like you have to understand that it's like really, really big, 40,000 like engineers, right? Or like it's massive. It's this big place, right? And they do so much stuff, and there's so much going on that like it's really, really hard to understand, especially for someone that does work like I do in infrastructure, how that like matters or relates to anything that the company does. So like I worked on, you know, their networks, and like networks are important for a company that serves web traffic, but like I don't know, I don't see exactly like why this specific thing that I'm doing today is like helpful for search or whatever, right? Stripe is like very different from that. It's much smaller. It's still a big company, like 4,000 people, but it's like 10 times smaller. So I can kind of see how I relate to the company. Also, Stripe is like newer. It's not as old as Google. And so it's like a lot more aggressive. There's a lot more focus on like completing things and doing stuff. So it's more fun for me at this phase of my career. Like, I think, you know, in the long term, if I wanted to have a place that kind of got a steady paycheck and I didn't have to worry about as much, like Google would be a better place. But yeah, I mean, I think both of those I would consider to be big tech for what it's worth. They're pretty similar in a lot of ways, you know, lots of organization, you have like 5 bosses or whatever, right? Like it's 5 bosses hierarchically is what I mean. I only have 1 direct boss. So yeah.
In regards to your application career, you have standout hindsight is 2020.
I do, but Oh, I don't, not to brag, but I think I did something really good, which was to not do a PhD. So I have a friend that went and did a PhD like at about the same time, and I feel kind of bad for them right now because the job market's not super great. And like after you invest all that time and energy into getting a PhD, like it's kind of rough to start in industry right now. But anyways, I think like, I did research for like 4 years roughly. So I did it as an undergraduate and then in my master's degree. And it was really fun. It was a good experience. I learned a lot, especially about like technical writing, giving presentations, stuff like that. But like, don't do a PhD unless you want to do it. Like, unless you yourself, like not just to get a title, but you have like some idea, some like specific thing that you want to spend 4 years of your life thinking about, like do a PhD. Otherwise, don't do it. Also, just people don't generally know this. It's kind of slightly unrelated, but if you go into like graduate studies at all, go into research or something, if you get a TA-ship or an RA-ship or do a PhD, you'll typically be paid. Like you'll have your school paid for and be paid. That's like pretty common in CS. So if you want to do those things, it's generally financially pretty achievable. Yeah. I don't know what OSU does, but that's the general practice. Cool. Thanks, everyone.